let's start with a blank sheet of paper here. And let's start with lines. And looking at it from 3 dimensions, you can also apply this in 2 dimensions. But if we take a look at lines, what are the 2 things that we need to come up with an equation of a line? Point and direction. You can do it with 2 points, but when you have 2 points, you're essentially going to find a direction between those 2 points. But in terms of what you really need, you need a point and a direction. And we'll fill this in a minute, but for a plane, what do we need? Do you remember? No. We need 3 points to begin with, at least 3 points, and they all lie in the plane. If you have 2 points, then that's not going to be enough to determine a plane. So you need 3 points. But in terms of coming up with an equation, what does it boil down to? What do we really need to come up with a what? A point and a normal vector. So if we want the direction that we're referring to, and the first one is actually direction vector. So we can elaborate on both of these ideas, and this is one of the things that you should have been working on with your, what's that called, the lab. We have a point, and I think the lab calls it R naught or something like that, but we'll call it P naught, it doesn't matter. And a direction. We'll call it V. Then you can express your line, we'll call it L of T. And technically, this is a vector, so I'm going to put an arrow in front of, on top of L. But we can change this as a function of t. We can write it in a few different ways. We can write P as a point from the origin, or as a vector from the origin to that point, plus a parameter t times a direction vector v. And each of these have components, so we could take a look at those components as well. In fact, I should have done that, sorry. Sorry for your notes. But if we have a point and a direction that looks like that, you can rewrite your equation in vector form and change that into parametric form. So I'm going to skip a couple of steps and just write it in parametric form with parentheses, and it'll be clear which one x, y, and z would be. So the x value would be x naught plus v1, this is an x, v1 times t, so that's your x of t. Your y of t is y naught plus v2t, and then your z of t is z naught plus v3t. So if you consider each one of these components as the x, the y, and the z, then you can look at it from the parametric equation point of view. And the plane, you need a point and a direction, not a direction, a normal vector. And so we can also approach this using vectors. If we let x equal to x, y, z and treat it like they were variables, then we can write this as the equation of the plane as the normal vector dotted with the variables equal the normal vector dotted with the point as a vector from the origin to that point. Now, if we fill in the components like we did with the line here and call this point x naught, y naught, z naught, and call this normal vector ABC, it's usually what it's called, then your equation then becomes ax plus by plus cz, that's your ABC dotted with x, y, z, equals to the dot product over here with the normal and the point, but that just ends up being d. Well, I think they use lowercase. I don't know. I happen to have used uppercase here. Where the d is equal to the dot product between the normal vector and the point, if you treat the point as a vector from the origin to that point. So this is our summary, and we found things like if we had 3 points, we can make 2 vectors out of those 3 points and then find the normal vector by crossing it, and then we have the equation of the plane from 3 points, and so that stuff we talked about last time. So I want to get a little bit deeper into studying lines and planes by finding intersections of things and finding distances of things. All right? So this is a summary review, and I hope you will be able to remember these equations and where they come from. If you understand where they came from, then remembering them would be easier. But if you just want to choose to memorize it, you can memorize it and just make sure you know what components to put in. But in general, for each of these things, you want 2 things, a point and the direction, or a point and a normal. Now, if you have 2 points for a line, you can still find the 2 points. You can find a direction that connects those 2 points, and then you have a point and a direction. Or if you have 3 points on a plane, like we did last time, we can find a normal vector from those 3 points, and then you can come up with your equation. All right, let's take a look now at some of the things that we're interested in doing. So we talked about 2 lines in space. We did a problem where they were skew or they intersected. I forgot what happened. But we talked about that. That's a very common problem. Now let's talk about planes in space. If you have 2 planes in space, and these planes are infinite planes, then there's only 2 possibilities. Or a third possibility might be there might be the exact same plane, but we'll not worry about that possibility. But the 2 general possibilities is that the planes are parallel, in which case they don't intersect, or if they do intersect, can you imagine how they intersect? If they do intersect, they intersect in a line. Look at your book, your notebook. Just open it up halfway or a quarter of the way, then it looks like 2 planes, and that binding where they meet would be their intersection. And that binding is a line, right? It's not like a curve or anything. It's a straight line in space somewhere. So Here's our task to find intersections of planes. Wait, can you find the line of intersection between two planes? Oh. Sorry, let's not do that yet. Let's focus on if two planes are parallel. So two planes are parallel. What would be a distinctive feature in that plane, in those two planes, that would allow you to show that they're parallel? Any ideas? Do you understand my question? There's going to be a distance between them, and the distance will be the same wherever you are. What else? Same normal? Maybe. Not absolute. Not the magnitude. So that's a thing that could be different. So it's not necessarily the exact same normal vector, but the normal vectors could be parallel to each other. If the normal vectors are parallel, right, then the planes are going to be parallel. So if the two planes are normal, if the normal vectors of the two planes are parallel, then the two planes themselves are going to be parallel. Right? If I twist one of these normal vectors a little bit, then the whole plane is going to have to be twisted also. Then these two planes will eventually intersect. Uh-oh, I didn't adjust that correctly. That's what I did, but weird things happen. And the normals don't have to be exactly the same. I mean, if they are, then that's a dead giveaway. But if they're linear combinations of each other, if you can write the first normal vector as a scalar multiple of the second normal vector, then they're the exact same direction. They're the same direction, so they're the same. Okay? I don't know if I can find an example of this. You get the idea. We don't need the example of this. Let's just go to the next one. Intersection. If two planes intersect, if two planes intersect, they're actually going to intersect in a line. Right? And if the two vectors are not parallel, then the two planes will have to intersect somehow, somewhere. So we can say one way to check if something's happening with lines, if two planes are not, if the normal vectors are not parallel to each other, then the two planes are not parallel, and if the two planes are not parallel, then they will intersect. Okay? And the object of intersection is going to be a line. So I guess one of the ideas for us to try to find is the equation of that line, how we're going to find that line. What do we need for an equation of a line? What are we going to need for an equation of a line? A point and a direction. Okay? So somehow we're going to need a point and a direction if we want to find the line of intersection. So I don't know which is going to be easier. I think they're both hard. But we'll try to find how we're going to find this intersection. We're going to try to find a way to get that equation of the line by finding a point and a direction. So let's start with a direction. Yeah, how are we going to find a direction? Okay, so we need a vector, right? If I'm looking at these two planes and I need the vector, I need this vector right here. Is there any way to find that vector? Do we have any vectors at all?
Could the green vector be the cross product of normal vectors for each plane?
Oh, I don't know. Can it? Let's see. We have one normal vector for one plane and another normal vector for the other plane. Okay? So the way I drew them, I just drew them randomly because you can move those vectors around to whatever you want. But let's say we have these two vectors, and what if we take those two vectors and we put them tail to tail on some intersection place? Well, what can you say about this line, the green vector or the red line? Tell me something interesting about that line.
Could be going in either direction.
Could be going in either direction. But tell me something about that line with respect to the planes. They're what? Tell me something about that line with respect to the planes. What? They're
all the points on the line are where the two planes are equal.
Yeah, so all the points on a line where the two planes are equal. So we could say that that whole line is actually on both planes, right? So that vector is going to be on both planes. So yeah, that's exactly what we're going to do, is we're going to cross them. So the cross of the normal vectors, this is normal. All right, let's make an effort here. Normal vectors is the direction of the line that you're looking for. And we can easily get the normal vectors, right? They're A, B, and C. They're coefficients of x, y, and z in your equation. And so if you cross them, you're going to get a direction vector. Direction vector, done. Now, finding the point is a little bit more difficult. And for this, we're going to show you some techniques that we haven't really talked about. And we probably should have talked about this when we first started talking in this section about a line that would eventually intersect a coordinate plane. Do you understand what I mean when I say coordinate plane? What's the coordinate planes? What are the coordinate planes? Kind of. X, Y, and Z, I think of, when you say X, Y, and Z, I think of that as an axis. X, Y, Z axis. The YZ, the XY, the XZ. So those are the coordinate planes. There's three coordinate planes, the XY, the YZ, and the XZ, or ZX. I'll tell you why it's called ZX later. But, so those are the three coordinate planes. Now, let's talk briefly about the YZ plane, the XY plane. The XY plane is the horizontal plane, right? What's the equation for that plane? Z is equal to 0. So it's XY plane. That means it's laying flat where the Z is equal to 0 is. So Z is equal to 0 is the equation for that plane, right? So we have the two planes. Let's call it AX. I'm going to call it AX plus BY plus CZ is equal to D. That's one plane. And then for the second plane, I hope this doesn't get too confusing, but I'm going to call it A prime X plus B prime Y plus C prime Z is equal to D prime. And those primes just say they're different numbers from the first set of numbers that we saw. So you have two equations, but you have three unknowns, right? So one way to find a point is to find out where these planes would eventually possibly intersect the XY plane. And the XY plane we just said was the equation Z is equal to 0. So if you let Z is equal to 0, and then you'll solve for XY, what you're going to get is the point where that line is going to intersect the XY plane. Okay? So that would be a way to find a point. Now, is there a scenario where this might not work? Think visually. Think about our two planes in space somewhere intersecting, intersects in a line. Is there any way that this line may not cross the XY plane? What? If it's parallel to the XY plane, then it's not going to cross the XY plane. So we might have an issue if it's parallel. So if this method doesn't work, what else can we do? Shoot for another variable. Let another variable equal to 0. Because if this doesn't cross the XY plane, it still has a possibility of crossing one of the other coordinate planes. Okay? Does that make sense? Yeah, maybe. Is it really confusing? Is it all visually like, whoa, what's third dimension and what's going on? And are you guys like blown away? No. This is kid stuff. Wait till we get to the next chapter. I'm just kidding. All right, let's see if we can find a problem where we find the intersection of two planes. I forgot to start up my WebAssign. Maybe I need to request an extension. Let's see. Plane, 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 plane. Here we go. We have two planes. It says find the point in which line intersects, but we can actually find the equation of the line. So let's just do that. Find a point at which the line intersects the given plane. Find the point. Oh, sorry. Wrong problem. I can't do that. That's a line and a plane, so that's different. Let's try again. All right, I think we found one. Number 37. So you have two planes, x plus y plus z is equal to 3. And then x plus 7y plus 7z is equal to 3. So those are two planes. If I, just by inspection, if I look at the normal vectors, 1, 1, 1 for the first one and 1, 7, 7 for the second one, I can already tell that they are not parallel. They're not collinear, so these planes are not parallel. So I'll call the first one, the normal vector for the first one, n1. And I'll call the normal vector for the second one n2. And then it's asking us to find parametric equations of the line of intersection. Use a parameter t. All right. So we need a line. We need a point and a direction. So remember, the direction vector that we want would be the cross product of the two normal vectors. And the cross of it, because the crossing is not commutative, it's going to give us different answers if we put one versus the other first. But since we're looking at the direction in general, it doesn't really matter which way the direction's going. So let's just cross N1, cross N2. So the direction, let's call it D. And it'll be the cross product of 1 and 2. And I hope you're comfortable with this already. Let's see if I could do it without using Wolfram alpha. I get 7 minus 7, and the j is 7 minus 1, which is 6, but it's negative. And then the k is 7 minus 1, which is positive 6. Did you guys get the same thing? What? Yeah? Okay, good. So that's my cross product. So remember what you're doing, right? You're just taking little submatrices and finding the 2 by 2 determinant of the submatrices. All right, so that's my direction vector. So the direction vector is done. Now I just need a point. So to find a point, I'm going to let z equal to 0. Let me just rewrite everything down here. X plus y plus z is equal to 3, and x plus 7y plus 7z is equal to 3. And I'm going to say let z is equal to 0. Okay? And then I have 2 equations and 2 unknowns. I should be able to solve for x and y. So maybe I'll put a minus sign in front of the top and then add them. So the addition method, I'm going to get 0, 7y minus y, that's 6y, plus 6y, and then 3 minus 3 is 0, so y is equal to 0. So I got z is equal to 0 and y is equal to 0, so let's find out what happens to the 3. Let me put it into the first equation. X plus y is equal to 0 plus z is equal to 0. So that gives me x is equal to 3. So that's my point. 3 for x. Zero for y, 0 for z. And if you want to be absolutely sure that that point is on both planes, you can plug 0 for x. I'm sorry, you plug 3 in for x, 0 for y, and 0 for z in both equations, and it should work. Can you do that in your heads? 3, that's 3. 0, 0, that's equal to 3. That's 3 in for x, 0, 0, that's equal to 3. So we're all good. All right, so we're basically done. Now that we have a point in a direction, your line is given by, oh, they want parametric form. So our line is going to be point plus t times a direction vector. So the point is 3 plus 0t. And then the next point is 0 minus 6t. And then the last one is 0 plus 6t. Right? All right, let me write it down. 3, 0, 0 plus t times 0 minus 6, 6. And then break it down to the different parts. Okay? Is that good? All right, since we're here and this problem is asking us to find the angle between the two planes, we might as well find the angle between the two planes. Any ideas how to find the angle between the two planes? What? What? Angle between the normal vectors. If you look at, you can do this with your books. If you take a look at the book and open it halfway and put normal vectors on that book, you see the angle between the normal vectors is the same as the angle between the book that's open. I guess more visually here, the angle between the two planes is the same as the angle between the normal vectors. So all we really have to do is find the angle between normal vectors. Do you remember how to find the angle between the normal vectors? Do you remember how to find the angle between two vectors?
Geometric definition where we use the vector 1 dotted with vector 2 is equal to the magnitude of vector 1 dotted with the magnitude of vector 2.
Good. So remember, when we want to find angles, the dot product gives us a little bit more surefire way of finding the angle between them. You can also find the angle using the cross product, but it involves the cross product. I mean, we have the cross product already. You have to find magnitudes and its sign. Sometimes the sign, finding the inverse sign of something is, it's easier to find the inverse cosine of something than it is to find the inverse sign. So if you remember the formula, that's great. If not, then too bad. I'll write the formula where the cosine is already by itself, and so that's the dot product between the two normal vectors. And then the magnitude of each of those normal vectors. So the two normal vectors are 1, 1, 1 and 1, 7, 7. So if you dot them, 1 plus 7 is 15. Positive, so we know that it's going to be acute. I don't know, because we have to take the the inverse cosine. The magnitude of 1, 1, 1 is root 3. Magnitude of 1, 1 or 177 is 49, 49, and 1. So 99, maybe. And then just take the inverse cosine of this. Anybody punch this in the calculator and give me the answer in degrees? Let's do degrees. Anybody confirm that? Make sure you're in degrees. A lot of times we want to set our stuff in radians. If you get your answer in radians, just multiply by some factor to write it in degrees. I think it's 180 over pi or something. Can we get a confirmation? Can we get an okay? Can we get an amen? I need another person. It's your answer, so I need another person, just one more person to say okay, and we'll move on. 29.4? Yeah? All right, good, thank you. Amen. All right, so that would be our angle in degrees. Okay? So that's how we find the line of intersection between two planes. All right, let's move on. What else do we need to do? Can you find a line of intersection between two planes? Can you find an intersection between a line and a plane? Let's try to find an intersection between a line and a plane. We actually had a problem like this that we were going to choose. I think that was number 30. So if you imagine a line in a plane, if you imagine that they intersect in space somewhere, then what are they going to intersect in? They're going to intersect in a point, right? So our task is to try to find the point of intersection. And whenever we want to find intersection of things, we tend to set something equal to something. You know, back in pre-calculus or algebra, we have two lines. We find the intersection of two lines by setting them equal to each other, right? Something like that. Set the y's equal to each other. So it's the same idea. We're going to set things equal to each other. But the idea of setting things equal to each other gets a little bit more complicated in 3D since we're playing with three variables. So what we need to do is we need to see what happens here. So I don't know exactly how these lines might look like, and the line and the line and the plane, but this is the point that we want, the point where they intersect. So in our attempt to try to set something equal to something, this is a little confusing for me because I have x, y, and there's two equal signs on this first one, and there's one equal sign here, and I have x, y, and z here. Any ideas?
Well, doesn't that just mean that x is equal to y minus 3 and x is also equal to 2z? So we could break that out into two different equations.
I suppose. And then we got these two equations, and we'll put it over here. It's not exactly what I was going for, but I don't know if that'll work. There's a chance it might work. I don't know. Here's my idea. The line may not look like it right now because what kind of equations are these? This is in symmetric form, they call it. And do you remember how symmetric form came about? Usually we look at lines and they're parameterized by t. So at some values over here, we usually look at the line as a function of t. When t is equal to 0, you're somewhere. When t is equal to 1, you're somewhere. When t is equal to -1, you're somewhere along that line, right? And so the way I'd like to think about this is to take your symmetric equation to see if you can pull back and somehow get the parameterized line out of that. And how can we do that? We can say, well, each of these things are set equal to each other as t. That's how we lost the parameter. So we can bring it back the same way. So x is equal to t, y minus 3 is equal to t, and 2z is equal to t. And then I will want to put the values of x, y, z into here. So I'll solve for x, y, and z. And now I'll take my equation of the line and drop my values for x, y, and z where x, y, and z belongs, but instead now put in a value of t there. So if I do that, what I'm going to have is an equation, one equation with one variable t, and then I should be able to solve for that, right? In fact, it's a linear equation, so this should be an easy solve. So let's see. We got 2t minus t minus 3 plus 3 halves t is equal to 2. 1 plus 3 halves is 5 halves. Bring the 3 over to the other side. So that's a 5. And t is equal to 2. What is that? What does t is equal to 2 mean to this picture, to this equation? What is it? Yeah, that's exactly it. So when t is equal to 2, that line is actually on the plane. But that's not your answer, right? You want your answer to be an x, y. You want your answer to be a point, x, y, z. So this is the time, if you want to look at parameter as time, this is a time when that line hits the plane. Let me write when a little bit clearer. This is a time when the line hits the plane. To actually find that equation where the line hits the plane, you need to plug that back into the L function. L of t, well actually that's this over here. So x is equal to t, y is equal to t plus 3, and z is equal to 1/2 t. So t was equal to 2. Then your point of intersection is going to be x is equal to 2, y is equal to 2 plus 3, and z is equal to 1/2 times 2. So 251 is your magic value. That's the point where it intersects. Now if you want to be absolutely sure, you know how in algebra we always check our work. This point is supposed to be on the plane. So if you put 5 in for x into your original plane equation, you put 2 in for x, 2 for x, 5 for y, and 1 for z, you should satisfy that plane equation. Okay? And it should work because that's where that thing came from. Any questions? Is this kind of fun? I'm not giving you visuals other than like generic drawings, but we can actually see this and I wanted to start using the free online graphing tool that you can use. But it's too hard. So it's not hard, but it's not as easy as this, I guess. All right, maybe we'll use that. Let's try. since I do want you to be able to visualize some of these things. Did I put a link for this in web access? There's a link. Okay, so there's a link for this in web access. You need the Java and all that stuff, and so just make sure that that's installed properly. So there's a couple ways to approach this, and since we haven't really gotten to chapter 14 yet, where they talk about functions in general, we can not use these function things. These function things describe equations where z is by itself. Now, because we're dealing with planes, I think it's easy enough to find z by itself. So let's take advantage of that idea. 2x minus y plus 3z. Oh, z. I have to solve for z. If you solve for z, 2x minus 3y what was it equal to? Equal to 2. Now they shrink it. So let's see. If I have a 2 minus 2x minus 3y and then have to divide by 3. It's going to give me an equation of a plane. Now I want to include a line in this picture, and the line here you can graph lines using parametric form. So our parametric form is going to be t plus 3, and 1/2 t, right? So let's open this up again. Parameters, graph a space curve. It's a line, but you can think about it as a curve. So x was equal to t, y is equal to, what was it again? T plus 3, and then z is equal to 1/2 t. And I know that my t is equal to 2 is when it's going to cross. So I have my t going from -10 to 10 here, so that's going to include 2. So I'll just have it graph. It's going to cross right here. Looks like it's going to cross right there. And so just to actually make sure that we got the point correct, I'm going to graph a point, add a point. And what was the point that we got? 2, 5, 1. Enter the size. Let's make it big. 9. More color too, red. Oh, that didn't work.
Is our equation incorrect?
Is it? Minus y? Plus y? Boy. Doing everything wrong. No? Oh, maybe I need to extend this. Where's my extend? See, I should have used the other program. Grid size, format axes. Here it goes. The intersection had 5 in it, right?
Correct.
Which one had 5?
Y.
The Y had 5. So just let's just include 5 here. Let's make this go up to 10. It's going to be all messed up. There it goes. It's on. Well, that wasn't a very good way to demonstrate how easy this is to use. This would be a better tool when we get to the next section where we do quatrics, because it allows us to graph what's called implicit functions. All right, we didn't find any distances yet, and so I think we're starting to fall behind with our subject here. And what we need to do is we need to find distances. So I think I'm just going to do 2 of these next time, and then we'll have to jump to the next section where we finish it off by looking at the different types of equations. And that screenshot over here, I'll try to get this copied off and then have it online so you can view it and download it if you want. I want to show you something else. This is things that calculus students never say.
But I wonder if I can take Calc 2 next semester. Do you want help with? Can you please skip more steps when you explain things? I don't think I deserve this partial credit. Calculus is my favorite class this semester. Good morning! It's not required, but I wonder if I can take Calc 2 next semester. Do you want help with your calculus homework? I totally understand the professor's accent. This is going to be so useful after college. Dude, Wolfram Alpha is so not helpful. This applies to so many things I do every day. Yes! All of the above and none of the above. I wish this test was earlier in the morning. I wish I could use cheating a little more often. I love sitting close to the front. I totally understand this. I can't wait for the next test. I wish we weren't allowed to use calculators. I'm so glad he assigned us the even problems so we can't look at the answers in the back of the book. I feel really good about the exam. Related rates problems make so much sense to me. Our textbook is just so light. I'm doing so great in this class. I think you gave me points for this, but I'm pretty sure I got it wrong. I kind of hope I don't pass this class, just so I can retake it. Wait, you forgot to assign his homework. I'm so relieved that the final exam is going to cover the whole semester. Can you explain an example faster? I hope the teacher calls on me. This homework's so easy. Yes, calculus!
All right. I just thought that was kind of funny. So yeah, so we got some stuff to work on. We're a little behind in our schedule, but we'll be caught up just in time for our next exam, our first exam.
Which is
2 weeks?